PI of the NSF grant to acquire and deploy Frontera, which is the largest system. Many of you must be using it, which is the fastest supercomputer at any US university. He also served as the PIs of the TAC Stampede 2, Wrangler, many of those earlier systems. And prior to that, he also served as a co-PI of Cybers, a large-scale NSF life sciences cyber infrastructure. And today, actually, he will be talking more on the next step. He's actually putting together a system which is called the Leadership Class Computing Facility. Okay. So with this, let's give a very hearty welcome to Dan.
Thank you. I'm now nervous about you bringing up my slides after. If you'd like to know how long we've been working together, that photo of me is a good example of things from decades ago. Less gray hair. Photoshop might have been involved, I don't know. There we go. Excellent. Okay, so I don't need it. Yeah, I just need to advance. Thanks. All right, well, DK, thank you very much for the kind invitation to be here and the warm introduction. And also, thanks for inviting me back. I think this is the 5th time I've been here in person, and counting the COVID years, probably the 7th or 8th time I've spoken at this. I didn't make it back last year for in person because DK scheduled my talk for 90 minutes after our NSF site visit for the leadership project ended. So sort of slipped out of one and into the other, but it's great to be back here in person, particularly in a place where I can wear a jacket and not spontaneously burst into flame, as Austin is on its 46th consecutive day today over 100 degrees. So the old record was 27. We have a good chance of doubling it. So fortunately, there's no change in the climate. So, but yes, this is 17 years that we've worked together with DK and with the Mbappage team broadly. So probably what, 3 generations of grad students at least through that, some of whom now work at TAC. We started with a machine called Ranger way back when. The proposal was awarded in 2006, so I guess we actually wrote it 2005. But the where we were building a giant machine from a company called Sun, which most of the grad students don't remember. And you know, we even at the time knew you never rely on the vendors for the libraries to make things work. You need partners who you can guarantee we could get performant communications from. And it turns out our Mbappage was much more performant than anything we could get out of the vendors at the time. So, so we've continued that through now 4 or 5 system projects, and you know, now onto the leadership facility, which we'll be working on for the next 12 or 13 years together. And if there's one thing I could get funding agencies to understand about how system software works, is it really is these sort of long-term collaborations that make stuff work. I mean, how many developers did you have 17 years ago working on this, student-wise? 5 or 6, maybe? Yeah. Now you were telling me last night there's what, 35 you know, on your team working on this, right? So we're, you know, from a grant support thing, they always want you to finish the software and then you get those benefits where you have less developers. In reality, the development team just grows and grows over time as the features add and the number of things you have to support adds and grows up. So it's been a remarkable collaboration that's now almost old enough to vote, and which will be important next year. And you know, I can't thank you enough for all that's been done in the way. So just 2 slides that I always show about us at TAC. So, yep, we are down in Austin. We are a large NSF funded center, like our partners from San Diego, several of whom are here. So we operate a host of different platforms for the National Science Foundation and a few locally for users in Texas and Texas industry, et cetera. We run a little over 1 million cores, about 1,000 GPUs. We have about 20,000 physical servers. We put out about 7 billion core hours per year. Most of you know all this. And in a few of the big systems, that's Stampede 2, which is being retired and replaced with a Stampede 3 I will talk about shortly. On your left, on your right is Frontera, which Doesn't look as impressive because it's in the back of the data center, whereas Stampede's in the front, so it has to have the good graphic. But the much denser Frontera, where everything's liquid cooled and 60 kilowatts a rack, which one day we'll look upon fondly as the days of nice, cool, low power racks. Yes, I also run in that Texas climate 9 megawatts of computers because I'm not that bright. So and then we'll replace Frontera in hypothetically 2 years, or whenever Congress gets around to passing the budget, which has no bearing on anything having to do with reality, with the leadership class computing facility funded by NSF, and a couple of years down the line. But because this is an MVAPIC meeting, the one thing we have to talk about for Frontera, yeah, it has processors and all that stuff, but is the interconnect. With Frontera, we use Mellanox, Glad's right there, HDR, in a fat tree topology. I'll talk a little bit more about topologies, why we do that a little later. We originally had 91 compute racks. We've since added 400 nodes as a result of some COVID funding to the machine, but at 88 nodes per rack. Another thing vendors very seldom seem to figure out is switch ports are expensive in InfiniBand. So what actually governs the way we lay out the racks is the radix of the switches that provide. So with 88 nodes per rack, and we're using two 40-port HDR switches in it, this machine was deployed in 2019, so it was Gen 3 PCI. You can only get 100 gigabits out of that PCI bus, so we're using HDR 100 cards in the nodes, but that means we could double the ports since those switches can do 200. So we used 22 ports for 44 nodes, so each half of the rack goes to one switch. Then 18 uplinks at 200 gig. So we have sort of an 11 to 9 oversubscription factor there. And then those 18 uplinks get split into 6 bundles of 3, which go to each of the 6 core switches. So we have 6 complete paths, sort of 6 parallel fat trees to get anywhere we want to go. And then we have no oversubscription. We're going to serve the storage nodes, the data transfer nodes, et cetera. That gives us about 8,500 endpoints. Now it's like 8,900 endpoints on the fabric. 182 top of rack switches, 6 core switches. There's about 50 miles of fiber to put that together, or 50 miles of cable. We use all copper in rack, so because we could do the 200 gig thing, we only had to run 3,300 fibers to put that machine together. But it's a pretty complicated interconnect with a lot of paths and a lot of sort of dynamic load across it. And you can't have an interconnect like that without a software stack. And as always, we rely pretty heavily on the team here at Ohio State for MVAPIC. And at least in this machine, we have some vendor alternatives that we can use in certain situations. That's going to be actually less and less true moving forward with the newer machines for reasons I'll talk about. But we're going to rely even more on MVAPIC. But Frontera, like Stampede before it, Stampede 2, Stampede 1, Ranger, all the machines we put up, is an opportunity to look at new scales for MVAPIC typically. We have more nodes, more cores. This machine has about 450,000 cores. New machine will be well over 1 million. And one of the reasons we partner is, of course, to get a working fabric and to push the fabric forward. The other is so we can tune for whatever crazy machine that we build next. With, this is a 56 cores per node. I'm still bitter at Intel over the not following the powers of two thing, but we have lots of tuning to do on collectives and things like that to bring it up. And in particular, we look at a lot of the monitoring and stuff you're going to hear about from Samir and from Gilad and various folks today, into how we can really understand and tune performance of this network. And MVAPIC is always huge in our doing acceptance. So when we actually accepted Frontera, we started out with some problems with a code called QMC pack. We ended up far exceeding our acceptance estimates on it because it is a code that NSF wanted to use for a benchmark system for reasons that dated to 2005, so very appropriate for a 2019 benchmark. It doesn't scale well, but it's all collectives and all small messages. And so it beat pretty badly the Intel MPI performance on this. it was validated on some older machines, but this is one of those examples where we probably see, if we use like a standard Ethernet, we're probably 50 times faster on the large scale runs because of MVAPITch and what it can do for us. But mostly I want to talk about, that's sort of a few minutes on things looking backwards, but I mostly want to talk about things moving forward. So Frontera was sort of phase one with some cobbled together funding mechanisms from the Office of Cyber Infrastructure to put it together. We're now we've actually finished the planning process and are in the work with Congress on funding process, which is much less fun, for the Leadership Class Computing Facility. And so, and it's called Leadership Class Computing Facility because somehow Oak Ridge and Argonne seem to have a lock in the government on Leadership Computing Facility. So, so they get the LCCF and we get this extra C until I can come up with a better name. But but provided by NSF, and this is transitioning from the sort of traditional program funding that the Office of Cyber Infrastructure does and NSF SICE to what is called NSF's really bad at acronyms, but they did LCCF, but what's called the MREFC fund, the Major Research, Major Research Equipment and Facilities Construction Fund, which is what funds the big telescopes and the Large Hadron Collider and LIGO, the Gravitational Wave Observatory, and all these sort of long-term pieces of infrastructure. The Arecibo telescope, which I actually just had to send a team with, which is being decommissioned after 50-something years, and I had to send a team down to go grab 6,000 tapes that were stored in the jungle in a room somewhere in Arecibo. And after operating since 1964, we got a tape that was labeled Tuesday. So again, pretend your file names matter in the future because, maybe 40 years from now, somebody's going to look at your file you named Tuesday and wonder why you did that. So that we now have to restore and figure out what's on it. So there's only a few thousand Tuesdays since 1964, so I'm sure we're going to figure that out. It's on an 8mm tape, so I'm pretty sure it was a Tuesday in the 90s. But but with this transition, we have a very long planning process. We put in the proposal for it in 2017. We've been through, with the team here, 3 phases of design, 3 sets of design reviews, 3 budget audits, and at, let's see, we officially started planning in 2019. We wrapped it up in March, which sets the speed record by 3 years for one of these going through NSF. Typically, it's 7 to 10 years to go through the planning process. And now we have to get appropriated, but more on that later. But the plan is there for the machine, and I'll tell you the tentative plan. It, of course, changes depending on when the budget gets allocated or not. But the idea is to make a long-term, sustained investment in computing for the community to use. Once we get up and running and out of the construction phase, there's a 10-year operational phase with a 10-year potential renewal. So it'll have its own building, so we don't have to be the renewal operator. But but to make a 20-year commitment to have consistent computing resources for science, for data challenges, for the other big instruments. We're working with the next generation very large array, and something we couldn't do in the sort of Stampede Frontera Ranger model where we had 4 years of funding and out is the VLA folks are starting construction in 2027 and they start operations in 2032 with a 10-year data run, and they're like, can you be our partner for data? We now have the ability to say yes to those sort of long-term scientific investments and data investments. So for the last few years, we've been sort of heads down designing this thing while operating the other machines, and figuring out what this is going to look like while the world changes around us. So and everything's sort of a moving target. I would say that for us, the interconnect is something that's only growing in importance when we talk about big systems. And for those of us who do HPC work and have for our whole careers, DK, me, et cetera, most of you in the room, they have really always been critical, right? And really, bandwidth's important, but latency is super important, right? Even more so. If we could have had less latency but more bandwidth, less latency and less bandwidth, we would have taken it, because lower latency is always better. At this point, I think 15% of our latency is speed of light in the fiber. So Gilad can't make the latency any better for me. I'm looking for that upgraded speed of light that he's supposed to deliver for me, but he's still working on it. So but it was sort of an only for us thing. And for a long time, particularly as the clouds were evolving, their story changes for whatever's convenient, but was you don't need all that expensive interconnect bandwidth. If you're not doing HPC, you shouldn't spend money on interconnect. You shouldn't spend all this ridiculous amounts of money on interconnect that was never really that much. But then AI came along and radically changed the equation in terms of I/O. So I stole this chart. There are many stolen charts in here, but this is stolen from Facebook Meta. So where they put a ton of bandwidth into their networks, right? Typically they're building at sort of one rail of network per GPU in a node. And this is for unnamed models that they don't want to disclose, cleverly named M1 through M4, for their AI models. The amount of time they spent basically spin locking, waiting for network. And you see, in the best case, with one model, it's only about 20%. In the worst case, it's almost 60% of the time that they spend on the computers that they're now dropping. What did I see? One vendor just spent 1.3 billion on GPUs to do their training data, and 57% of the time, up to 57% of the time, those GPUs don't do anything because they're waiting around for the interconnect and communicating back and forth. And so you probably don't want to tell the venture capitalists who gave you 1.3 billion that you're spending 60% of the time idle on those things. So, so when we look at the AI workloads, now, not only does latency matter, and latency still matters just as much as it always does, but bandwidth seems to matter too. And more injection bandwidth and bisection bandwidth is incredibly important. So, and in fact, this was a bit surprising. I think that at this point, most would acknowledge that for the big AI workloads, the interconnect's even more important than it is in HPC. And just since no one has had a venture capitalist drop 1.3 billion on an HPC machine for their product training lately, AI is sort of the 800-pound gorilla to our sort of modest-sized chimpanzee in HPC. So I think one of the interesting things here is this is unleashing a lot of new investments in networking and the way we build things. So thank you very much. Good to see you. You know, the interconnect is steadily more important. And now we start to hear from vendors. I talked last year a little bit about, you know, examining disaggregation, who want to, you know, put more networks in the machine. And I constantly point out that one problem with putting more networks in the machine is there's no place to put them. As we get to tens of kilowatts per rack, these are the core switches out of Frontera. You note they have an awful lot of cable in them to make all that work. They're already liquid cooled. These are InfiniBand switches from Mellanox/NVIDIA. And for us, we can't really tune interconnects for sort of single application. So we're a user facility. We run thousands of codes, right? So, and we find having, you know, we must have a high-speed interconnect for the vast majority of those codes. And frankly, even if we didn't have message passing, we need it for I/O at this point. But typically we put in two in the machines. One Ethernet, so we have a way to manage when everything else fails. Do we use it to, we don't really invest in the Ethernet. It's cheap and oversubscribed, at least in past systems for the most part. I think that's going to change likely, but and then we use something like InfiniBand, or we still have some systems doing OmniPath. I know the Cornelis folks are here. We've looked at Rockport, but something else as a high bandwidth network, right? That we try and do fat trees. We try and not do much oversubscription. Yeah, we're bringing, this is sort of another difference from typical cloud pre-AI architectures, that we bring about 7 terabits a second off the top of the rack. 36 to 200 gigabit links, whereas they're much more oversubscribed. Again, that sub-microsecond latency, putting this all together, particularly with what we have to do with cooling, where we have to put, you know, now that's a liquid-cooled rack in Frontera, where you see we have the, it's a little bit dark, but there's a bunch of InfiniBand cable behind the liquid manifold, where we're bringing in the electric cooling in and out. We also have some machines where we do immersion, and then we're running the Ethernet and the InfiniBand. The InfiniBand's all black copper there. The Ethernet stands out as the yellow, but you know, that's an 84 node rack. That's an 88 node rack. The immersed one here is actually 70 kilowatts a rack. But you know, fitting more interconnects in and more rails of interconnect is just physically not going to happen. So we have stuck with the notion of, you know, one fast interconnect, not multiple multi-purpose interconnects. Again, as I mentioned, latency is our dominant driver for the MPI jobs, which is only 45% of the jobs that run on the system, but it's or many rails. It's physically hard to do in these boxes. So we have a lot of options. Well, we have more options than we did for a couple of years moving forward with interconnects, and you know, this is us thinking forward towards what we were going to put in the next system. The sort of standard ones are InfiniBand. OPA is back. OPA was around. OPA was sort of less around, and now with Cornelis, there's Performant and new OPA out there. There's Slingshot from HP/Cray, but that's sort of limited to HP/Cray. There's some startups like Rockport. Increasingly, I think, because of this AI driver, there's a lot of low latency Ethernet out there. Mellanox has traditionally always had the best Ethernet NICs in addition to the best InfiniBand NICs. But now we see lots of low latency Ethernet being pushed from sort of traditional network vendors to less traditional network vendors like Amazon, building out low latency interconnects. So to some extent, we have several options to pick from moving forward. There are a lot of concerns about this. You know, will Slingshot ever be available outside of a system you buy from HP, and usually a very tightly integrated large-scale system that's, you know, the entry level for a HP Cray type rack now is a 400 kilowatt rack that's physically about 4 times the size of a normal rack. So your sort of entry point for Slingshot is $1 million. So it's probably not going to be the choice of dozens of campus clusters, right, that mirror that software stack. Mellanox is aligned with NVIDIA now. So what do you do if you want to build a system with AMD necessarily? It's technically it all still works, but you know, is that going to be always true in the future is an interesting question. So I think, you know, there's the technical reasons we want to make a decision for a new interconnect, but the market reasons may be bigger drivers for us. We need to think about endpoints. We need to think about how much of the budget we can have, and then we need to think about, are some of these new options, are they viable? So let's just talk about a couple of things there really quickly. So for the most part, again, direct consequence of AI, big systems, the heterogeneous systems where we're putting in a lot of GPUs, we've actually seen node counts decline. But for a lot of the big systems, particularly if you look at like the exascale systems, which I'll use for reference in a couple of things, the rails per node are going up. So endpoints may be increasing, right? So I think one interesting question, if you want to write papers around it, is are we better off with a quad CPU, quad GPU node with 4 network rails, or 1 CPU and 1 GPU and 1 network rail on a simpler node, and then you just use 4 of them? Again, the trade-off there is, for the way they want to do big shared memory models right now, you have the faster NVLink interconnect in node. But if we're going to do that, we should either bring it out of the node or just make the whole thing InfiniBand. And not worry about the NVLink, because at some scale, you're going to have to go multi-node anyway. So maybe figure that out. But so yes, distributed memory is required if you're going to do that. So, but you know, in that case, even a 4,000 node system is going to have 16,000 endpoints. If you look at the biggest one I'm aware of right now, Aurora, up at Argonne in Chicago, they have, what is it, close to 11,000 nodes, 10,600 something nodes, right? But the, I think 10,624, but the, they have 6 Intel GPUs per node, so they put in 6 Slingshot rails per node, which means they have, with 10,000 nodes, almost 64,000 endpoints in the network to tune. But groups of 6 go to the same node, but different devices on the node in the same memory space. I suspect, you know, we know all that hardware got installed a few months ago. Tuning on that is going to take a long time, is my guess, right? It's just an enormously complicated machine. But nonetheless, so in general, node counts are going down. That, you know, Aurora, $600 million machine. Ronis will talk about. I don't know if he's still coming to talk about tomorrow. Let's talk about El Capitan. The Frontier system at Oak Ridge is 4 rails per node, I believe, so maybe 6. But less nodes, so we're going to have less nodes, but maybe more endpoints. So, you know, we need to start thinking about tens of thousands of endpoints. And then we need to think about, if we put in tens of thousands of endpoints, can we actually afford that? You know, one thing you'll notice is that GPUs, particularly because there's one legit vendor for AI in that who has a supply constraint, so prices are effectively infinite at the moment and scaling up, which means with node prices going up, the interconnects can take the same percentage at a much higher number. And so we've seen interconnect prices creeping up. And, you know, there's some questions as to that, is that sustainable? But there are clever ways we could think about maybe reducing the number of rails, right? One is obviously good distributed memory algorithms. I think in AI, where there's a lot of large messages, right? This doesn't really make sense if you're sending, you know, 16-byte barrier messages, but if you're doing large messages over MPI, compression is almost free, particularly if you do something crazy like put processing in the network path, which I'm confident is what Galad's going to talk about in a couple hours, is having DPUs in. You get essentially free compression at that point, or even if you just look at, you know, the new AMD things where we're going to have 192 cores per node or 192 cores per socket in the not terribly distant future, then taking a couple of cores to do compression effectively makes your network faster. And again, you can do it in real time. You can do it for essentially free versus, because you can't find ways to use all those cores effectively in the computation. But I think it's worth looking at, since we're here mostly to talk about network libraries, is how much is it the physical network versus the library or the application that gives you performance? And this is a really hard question to untangle. So we're just going to do it here with a couple of quick examples in the context of AI, right? And your mileage may vary in HPC things where there's so much variation in the codes. But right offhand, I'd say it's not really the application frameworks that make much difference. This is, you know, scaling out to 500 GPUs on a distributed memory system. And by the way, if this hasn't been said, if you look at DeepSpeed or Horovod or any of the things training the large language models today, you know, whether it's ChatGPT or any of the new big ones, under the covers, they're all MPI, right? So I think in the end, the MPI standard and our various implementations of it will be one of the great open source contributions to AI is the fact that they, after taking a few stabs at doing it themselves, like they did with everything else and reinventing various wheels, let's write low latency network code in Python, for instance. But they eventually figured out adopt MPI, right, and adopt fast interconnects, and that's the way to do it. So, so this is a comparison from a paper that I stole that, who knows, maybe the author's here. By the way, I was looking for InfiniBand benchmarking papers, and probably largely thanks to this team, about half the ones I could find were all citing our systems as the example for it, so that was cool. But this is from a group et al., and it just came out in June, and it's looking at large-scale performance analysis of the distributed frameworks. So again, these are all MPI applications, really, and they had their modifications to Torch versus Horovod versus DeepSpeed, and the lines sort of move around a little bit versus Ideal, but really, that's the same shape, and to first order, roughly the same performance, right? So they're all MPI implementations. They're probably using the same MPI in this case, which is why they just don't vary that much, right? Horovod, DeepSpeed, PyTorch, whatever. So, so from this example, maybe it's not the application frameworks, it's something else. Surprisingly, it may only be a limited amount the hardware, and it's more about how you tune the library and the fabric. So I found this one interesting. Again, unbiased source, it comes from Broadcom, who's a network vendor and who is here. But this can get every vendor in the room mad. So, but this looks at latency, and you know, if the bottom line was InfiniBand and the top line was Ethernet, that's what we'd all expect, right, for Blue. And the top line is normal Ethernet with normal configuration, and then scaling message size out to something big, 4 megabyte messages. And again, AI tends towards the larger messages, whereas HPC tends towards the shorter messages. And you see that, of course, regular Ethernet sucks, but if you tune it, there's actually 2 lines on the bottom, and one is a tightly tuned Rocky Ethernet system. So it's physically still Ethernet, and the other one is InfiniBand. And of course, they used a log scale, so you can't see the small differences in the lines where, InfiniBand may still have a 10, 20% advantage. And they used 100 gig in both cases. And again, if we were looking at an HPC benchmark, it may not look quite like this, but they've shown, at least for this case, where, with the right protocols and the right libraries and communication software fabrics, you can make Ethernet physicals, and InfiniBand physicals have at least similar latencies, right? So it may be all about the communication libraries and, of course, the associated protocols, because you're not doing TCP IP to do Rocky and all the things to make that happen. So to get the latency down, getting rid of some of those three-way handshakes and fun stuff like that that drive it through the roof. So, and again, this is just directly connected, so it's not a real fabric. If you look at a big fabric, you're going to get more difference most likely. But still, there's cases where with the network cards and maybe one switch port, you can at least get somewhat close. So, maybe libraries are where the action's at, because it's not the applications and it may not be the hardware. That means it's all about you guys and the software and communication libraries and the people who do software, the vendors for those networks. So let me just say a couple things about topology as we get into the next system. And we will, in fact, finish on time. I didn't bring my usual 65 slides, DK. So we've typically built fat trees. As I mentioned with Frontera, we usually do a little bit of oversubscription, not necessarily a ton of oversubscription. We're more or less going to stop at this point. So, and we only do that oversubscription at the top level. Node to node in the rack is never oversubscribed. But the conventional wisdom will tell you that a fat tree is the most expensive network. And that if you use more exotic topologies, you can save a bunch of money while getting most of the performance back. The problem with that theory is I've never actually seen that savings materialize for us. And in fact, if you look at the big dragonflies and other flies and various kinds of networks out there, butterflies, in the big systems, again, like the Crays, it saves Cray a bunch of money to not put all those switches out there. But they won't quote me a fat tree, so it's still usually my most expensive option. So we've always been able to build a fat tree, which the other ones are just trying to get close to and have hotspots for, like, say, where you put the I/O in versus the sort of full balance performance of a fat tree. I've never gotten a quote where somebody's version is cheaper than the fat tree version I was building. So I think it makes vendors more money to have topologies, but for us, we're going to stick with fat trees for the time being. However, we're having more heterogeneous systems, and it's not going to surprise you that the new system will have both GPU nodes and CPU nodes. So if I look at what we're doing for our next system for LCCF, and by the way, there's a serious shortage on the internet of full fat trees in pictures. So when I went to find clip art of a full fat tree, I had these lousy pictures, but things to work on. So, but we're going to have a set of CPU nodes in a non-blocking fat tree, no oversubscription anywhere to the top of that tree. We're going to have the GPU nodes in another non-blocking tree. And our theory is there's not a whole lot of stuff that's going to run on both kinds of nodes. And these are both fairly sizable partitions. So we are going to go up to a core network at one more level of fat tree, but we're going to oversubscribe there because really we don't think we're going to see a lot of inter-job communication across that ever. And if it's happening, it's mostly a stunt. We literally never see it now in our heterogeneous system. So we'll put the storage in there, but we'll have way more bandwidth. The storage, we only need a few hundred terabits. Only a few hundred terabits is one of those things you didn't say in the 90s. But our max, we need about 20 terabytes a second of bandwidth to make sure we can max out the storage. So we'll have a storage network, and then we'll have these two trees going on. So let's talk about the next system for my last few minutes here. So I will say, especially because this is going out online and being recorded, that we have a plan, but we're in budget limbo. And until Kevin McCarthy and Mitch McConnell give me my start date, it's tough to really have true final choices in technology. So we have a plan A based on the original projected schedule, but then we have lots of other plans whenever, for shifting 3 months, 6 months, 12 months, et cetera, on when things actually come through. So what I'm going to show you is using a planned start date, but again, you know, when the budget, you know, when we're talking about a budget shutdown at the end of next month, which will happen, and then a continuing resolution, which will happen. They think they're great politicians, but you can forecast this all in advance. And then there'll be a 48-hour mad scramble when they hit some collective deal on an omnibus somewhere around Christmas or New Year's. And then what gets in, and if you're not in that 48 hours, you're probably screwed. So the so what I'm going to show you is based on our most likely projected date, but all the technologies I'm going to show you could change based on vendor roadmaps changing, based on our in-house experience, but mostly based on Congress and budget. So based on us actually starting in this fiscal year, getting a March 2024 start date, which has been the planned thing for 6 years, which would, by the time we build the data center, give us a July 2025 delivery date. We're looking at a system where those two kinds of nodes would be primarily the NVIDIA next generation Grace for the CPU nodes and Grace Hopper for the GPU nodes. That will give us about a 20% of our performance coming from CPUs and 80% from the GPUs. To do that, and I'm going to follow up on this in a minute, but that means we're spending 60% of the money on the CPU nodes and 40% on the GPU nodes, based on what we see in sort of the software that's out there, although that's a bigger, so it's a bigger investment than we've made in the past in GPUs. It's still dwarfed by the investment that DOE is making in the exascale systems, where 97 to 99% of the performance is coming from the GPUs at this point. If you look at Frontier, it's like 1% CPU, 99% GPU. You basically sit and run CPU codes on it. We are maintaining, committed to our users that we'll have at least 1 million cores of CPU on this machine. So it will be a pretty big CPU machine that's going to give us, our goal was to do 10x of Frontera. This will do that in peak double precision 64 performance. We'll hit about 400 petaflops. If you look at the AI performance, where, you know, it's the 16-bit and lower precisions that matter, we're going to be at about 10 exaflops projected for bfloat 16. For that 400 petaflops, we're going to put in 400 petabytes of storage, all of which will be solid state. There'll be no spinning anywhere in that to make that happen. We're certainly not going to run Intel MPI on a NVIDIA Grace system, so MVAPIC is going to be our primary communications library and the one that we will rely on. But if you look at the big exascale systems that are out there, Aurora, Frontier today, the system's going to be, one, because of our huge advantage at low precision, we're actually going to be faster than Frontier on AI-related things, the current #1 in the world. We're going to have a faster I/O subsystem that's all solid state, and we're going to be way faster on anything that just runs on CPUs for sort of your traditional HPC thing. They will have higher double precision GPU performance by far. So again, remember, all of this is based on a budget scenario that may or may not happen, right? So, which this says again, because I just can't say it enough times, right? So, we think with the sort of multi-GPU coupling with Grace and some interesting ability to manage power, that we can actually deliver all this and keep the system power below 9 megawatts, which is about half of what Frontier is now, and it's about a fifth of what I think Aurora is going to hit. You know, it should be in the low 40s when they actually run their benchmarks. So this does involve us switching to ARM. So that's a big switch, right, on the CPU side, and a big ecosystem switch, but so that is a risk for us, and but there's two parts to that. One is, it's not just NVIDIA who's pushing ARM as the CPU at this point. It's the entire mobile space. It's Apple, the Mac I wrote this talk on, where I already run Rocky 9 on ARM in a container. It's Amazon, you know, it's the mobile space, right? NVIDIA, Apple, and Amazon, their market cap is higher than the revenue of the federal government. So the there's sort of a big investment pushing in ARM. But the other thing about that is, we also think at this point that it's lower risk to change our ARM, our CPUs to ARM, than it is to change our GPUs to one of the other options, where we don't have a lot of proof that things work yet, and we don't have the maturity that NVIDIA has on the software side for the GPUs. So again, the Exascale project is pushing that for a set of codes, but not everything's there yet. So we feel more comfortable with this scenario at the moment. So This is just the primary system, and we're going to build a bridge system I'll talk about in a second called Vista before Horizon goes online. And for DOE people in the audience, when we do refresh systems for LCCF, we're talking Pioneer and Zenith. So since you stole my name for Frontier, you can't have those. Those are all mine. Horizon, Pioneer, Zenith, Vista. That gets us through 2036. After that, you know, you can have whatever names you want. So the but again, Horizon is one of the systems we will have in LCCF. There also will be 4 other systems distributed around the country with some staffing and some hardware, each with a different focus at the other NSF-funded supercomputer centers, NCSA, San Diego Supercomputer Center, PSC, Pittsburgh Supercomputer Center, each with different focuses. PSC is really going to work on the I/O and storage piece. San Diego's worried about sort of high throughput instruments, you know, Frank is there, Open Science Grid, those kinds of things, high throughput for inference for things like Large Hadron Collider and those type of projects. NCSA is really working on particularly the match between accelerators and I/O and accelerators and network on their part of the system. And then we have the Atlanta University Consortium, which is a whole bunch of the HBCUs and an historically black medical school in Atlanta, focusing on sort of data science curriculum and accessibility and interactive workloads to put out there. So again, those of you who know tax systems know this is a much bigger investment in GPUs than we've made. And so why are we doing this level of investment? So because yeah, we can get the most flops that way, but that's really not the only reason to do it, right? So one is we've seen steady progress with our user base in terms of GPU codes. Obviously, everything in that 800-pound gorilla I mentioned, I don't know how that, yes, deep learning codes, right? Not all AI is deep learning, but it's a lot of it, right? And everything deep learning is GPU native, right? So those run way better on GPUs because they were built there. In our survey of our users, about 40% of our scientific applications have successfully moved, hence my 40% investment there. But that means 60% of them still haven't, particularly in things like astrophysics. A lot of the, you know, have a big project right now where we're looking at molten salt reactors. Most of those codes haven't moved. There is one ECP code that's sort of like that, but it's not the one most people use. So hence we're keeping that 1 million cores of CPU and the 60% investment. But we do feel like that, you know, in many ways, the DOE is pushing the community hardest on this, and they're right for a number of reasons. So we want to keep pushing our community down this path too, just not as hard as DOE, but for the same reasons, which is that power performance ratio is really compelling in GPU's favor right now. These are slightly dated numbers, but if you just take what in the spring was openly on the market where I could openly talk about numbers, so A100 versus AMD Milan and Intel Ice Lake. You can measure the flops, and you know, peak flops are a myth, but they're a myth for everybody. So, and there's 2 kinds of ways to measure GPU peak flops that are both mythical with and without the tensor cores. But if you look at the gigaflops per watt, the CPUs, and this is pretty much true across generations, are coming in at about 10 gigaflops per watt. You can also, I did flops per byte there too. And the GPUs are coming in much higher, right? You see why Frontier is based on the MI250, because they're getting 85 gigaflops per watt, 8 times better than they could get out of a CPU system. And if you look at sustainability, or you just look at the cost of electricity, if you prefer, for these things, that factor of 8, and you know, for typicals, it's more like 5 or 6. But you also notice the A100 is the most balanced in terms of memory bandwidth that you can get, you know, flops per byte of memory bandwidth, but the lower is better. You really want that number to be 1, ideally. So, you know, GPU prices are up, the cost advantage isn't necessarily that clear, but the power advantage is huge. And, you know, I'm still in Texas, power's fairly affordable, but we are gonna be spending $7-8 million a year to run the system on electricity. You know, the more we can use the stuff, the more sustainable we're going to be. So there's just a huge reason to push in this direction in the long term. So, but at the same time, because plans may change and dates may change, we're still pushing this general direction, but we're actually doing it through 3 machines at the moment that we're doing in the short term. So we announced just a few weeks ago Stampede 3 at the PERC conference. So which will be our primary Intel-based platform. And in that one, we're doing a lot of Sapphire Rapids with the integrated high bandwidth memory. We are putting in our first 80 Ponte Vecchios to try and develop some other GPUs that kind of work. We're also going to hang on to some of the Ice Lake and Xeon and newer Skylake nodes from Stampede 2 that aren't quite dead yet for the throughput case, so that'll give us about 2,000 nodes. We're going to go with OmniPath as our interconnect here, both to repurpose some of the older OmniPath we have in Stampede, but then the new 400 gigabit when that comes out. So that will be sort of our big OmniPath footprint. We're doing Vista, which actually for us will likely not be a Dell system because Dell doesn't have a Grace Hopper platform yet. So, but that's our big NVIDIA investment that we're going to make. Probably that machine will go in December when the Grace nodes start shipping, and I can find somebody to, not Dell, to put metal around it, but that's going to be our next generation InfiniBand investment, Grace Hopper. So it'll follow that path further on and all be InfiniBand. And then Lone Star 6 is our AMD platform that we actually did last year, but when Bronis stopped stealing all the APUs that exist on the planet, I'm going to put some of those in there too, the MI300s from AMD. That's also an InfiniBand connected system. So we'll have a non-Dell, we'll have a non-InfiniBand, we'll have all of Intel, NVIDIA, and AMD CPUs coming out. So all of these platforms should be available by the end of the year. Lone Star already is. And all at the sort of 500 to 800 node scale for the new technology for you to benchmark and with all three kinds of GPUs. And then one last thing I want to say with 2 minutes to go. I was going to really finish on time, but you started me late, DK. So everybody knows that porting to a GPU means using CUDA or OneAPI or something, HIP, et cetera, to get over there, or Cocos or Raja. It certainly means, a lot of the work that's been done around GPU Direct and tightly coupling the communication libraries. You get all that nice new memory bandwidth, which now actually we can get on a CPU too, and we're seeing how much that matters and have some numbers on that. But a thing that I think is underappreciated that we need to pay more attention to in HPC, again, for those looking for thesis papers to write, is that there's sort of nonlinearity in performance as the precision decreases, right? And that's going to continue because that's what AI wants, and what AI wants they're going to get. And so we're going to have AI-focused hardware we need to use for scientific computing, right? Just the way we used commodity processors way back when to do it. So if you look at the Hopper H100, all public data that you can pull off their website, at FP64, it's 34 teraflops. If you use the tensor cores, you get 67 teraflops, 2 to 1, that's great. If you look at FP32, that's about double FP64, that's what we've always seen, right? But now look at the 32-bit tensor core is 989 teraflops, right? It's 15 times faster than the FP32 vector performance, right? So if we can use these sort of matrix operations, right, and then you work your way up to FP8, which is at 8 bits, you might as well just guess, but right, but that's like 4 petaflops at that stage for one card, right? So there's potentially, if we could do things with 16 32-bit math somewhere in the middle of our algorithms and do mixed precision that you've seen Jack Dungara doing, David Keyes doing recently, we're not going to get the 2 to 1 that we used to get out of mixing single and double. We're going to get 15 to 1, right? And with the cost of these things, the 15 to 1 or even 30 to 1 when you get to 16, right? That's a huge advantage. So even if you have a less efficient algorithm, but you can mix the precision together, mixed precision algorithms are going to be where it's at because that's where the hardware is going. So I'm now officially out of time. So let me thank the National Science Foundation, UT, our many vendor and university partners, but especially the team here at Ohio State and MVAPICH, who again, we've worked with for 17 years. It really makes the systems go. As we have more and more exotic systems and more heterogeneous systems and multi-vendor systems, it's still the one library that's gonna make our systems go. So with that, I will stop and say thank you.
Thank you. We have some time for questions. Anybody?
DK's trying to make his talk shorter. Yeah.
I have a lot of slides. Yeah.
I know.
Please use the microphone.
Coming your way.
I was curious, what's the budget for Horizon?
So we've actually divided up the I/O in the system, but the primary system budget is around 135 million, and then The IO side is about another 25 million. And then there's some starter system and interactive system pieces, but firewall, stuff like that. So yeah, but the two primary compute parts, it's about 160.
In some other systems that go to ARM needing to have some complicated, half the login nodes are x86 to get certain things to run and things like that, like what they did with the Fugaku machine. Are you looking at options like that? Do you think you have a plan for getting all of the kind of analysis tools that you need ported to ARM, or what does the situation look like for that?
Yeah, in short, no, we're not going to put any x86 in the machine, except maybe in the storage path. But we want to make everything in the ARM ecosystem here. And again, we'll start that with Vista, and then we have a couple years to get it ready for Horizon. The application codes we've done pretty well on, the basic compilers and tools. We have some debuggers now that we've moved over there. We still have a lot of work to do on performance counters, right? And the performance counters aren't even going to be the same really as the Fugaku, the NEC ARMs, right? Because these ARMs are somewhat different. They are very close to the Amazon ones, so that's useful. But yeah, I think we'll be working with Samir and others on performance tools is really probably our biggest gap on ARM right now. So that's what the next couple of years is going to be, is to try and get that together. But our goal, I've seen systems that are sort of half x86, well, there's some coming, right, that are like half x86 and half Grace Hopper. But that means multiple compiler stacks, multiple binaries in your home directory, right? It's going to be just awfully confusing. So we feel like this is enough change. So we're going to try and build everything in the ARM environment and make it work. And like I said, we've done enough work that I feel pretty good about it, but there's a lot of work left to do over the next couple of years. And I think performance profilers and tools are one of the big gaps. Yeah. Also good thesis topics down here. Oh, Mike is coming.
Question on the power performance number. If I understand it correctly, you mentioned that you have about 9 megawatts the power target for the next generation, the Horizon systems,
Yeah.
which is less than half of the power consumption than the Frontier, right? Frontier consumes more than 20 watts as of now. So can you elaborate a little more on, so what makes you think that the Grace or the Grace Hopper system becomes that much power efficient, while the H100 is not necessarily more power efficient than the MI250?
Yep, I think a lot of it is the packaging. So one is, of course, we're getting the next generation, so we have the advantage of a couple of years and some silicon process and power, which is at least a little bit. We're also not spending 500 million, so I'm not going to have as many nodes as Frontier, which will help with that. But the other thing is, there's some really clever stuff going into the Grace Hopper modules and the next gen ones, where I think they've already announced that if you look at, they're looking at multi-GPU and multi-CPU modules. And I think one of the sort of underappreciated things there is when you do that, say put a CPU and a couple of GPUs on one of these single boards, you're power capping the board, right? So I don't have to build data center infrastructure for the theoretical max power of the individual discrete CPUs and individual discrete GPUs, because I know I can limit the power into that module, right? And we also know there is no single code that I can use where I can max out the CPU power and the GPU power simultaneously. With crazy virtualization, I might be able to come up with enough workloads to do that, but but what we're going to do is actually throttle at that sort of daughter card level, the module, and so and we'll just sort of dynamically reapportion power based on the actual workloads that we're seeing between the CPU and the GPUs on the module. So we will actually have, if I took the individual Hopper Next pieces and the individual Grace Next pieces and put them in, my total power would be much higher, but I know I can throttle it at that board level, so I don't have to build that back out through the data center, all that extra power, and that's going to help, I think, a fair amount in efficiency. It means we're probably going to run closer to our rated max power most of the time than we do now, right? Because, in fact, that's gone up anyway over the years. It used to be a typical workload would use maybe 50% of peak power, right? So Frontera is like now 70 something, right? It's 6 megawatts running LinPack. It's 4.5 megawatts on, 4 to 4.5 on a typical day, right? Running regular user codes. I think that gap is going to narrow because, we'll be giving them to whatever's stressed on that module is going to get the power that's available. But by capping it at the module level, I think we're going to have more efficient power management than we have today. And in general, just as one example, we'll have the LPDDR memory versus putting in a bunch of DIMMs, right? And the way that with AMD and Intel CPUs, we've been scaling memory bandwidth is to add more DIMM channels, right? So now you have, I think on the newest ones, you have up to 12 channels per socket, right? So I have 24 8-watt DIMMs, right? And the Grace modules, our memory power is only going to be about 40 watts, right? Versus 200 to 250 watts on a traditional CPU node. About 100 now, it'll be about 250 then, right? So, but that's, that's back just in memory power, right? So tighter integration is going to give us some big power savings versus the, traditional discrete part savings, right? But just GPU to CPU is already one big piece, and now the integration is going to give us another. Yes, sir. Yeah, when the actual construction funding starts, we'll be adding somewhat to the staff, and that is a focus. To do that, we have a lot of projects outside the core systems. Tax staff is almost 200 today, although really only there's about 20, 25 who are good at that kind of thing. But yeah, we'll be scaling up some on that, and of course, obviously, some of that is getting pushed back to the user community. And we're really counting on help from NVIDIA, help from Amazon and various places to make that happen. But yeah, we're going to start it with Vista, hopefully by the end of the year, certainly first quarter next year. And then ideally, when construction funding starts at March, we can go full bore on staff. And so we'll have a year and a half to get ready with full staff for that transition. Mm-hmm.
Any other questions? I have a quick comment and a question. Okay. So first of all, Dan, I'd like to
making your talk shorter.
Yeah. I'd like to thank again our long partnership, especially on behalf of the students. As you deploy these systems, that gives good problems for the students to solve. And especially when deadline comes, as I would like to
quickly.
So I'd like to thank not only to you and your staff member quickly giving us access, making reservations so that we can actually have very good papers and then convert those into the software. So that is the kind of, I would like to indicate that we have a very good relationship with them. The second question is, as you are deploying all these complex systems, or you have been managing also so many systems, what keeps you awake in the night?
Right now, it's the Commerce Justice Science Bill at the House, because those three things are linked together, and you know how one party is really eager to give more money to the Justice Department right now, and we have to get the top line number in that bill right. But so honestly, believe it or not, that keeps me up more than anything else at the moment. But and the extremely reliable track record of vendors delivering stuff on time is always something that I'm don't have to worry about. And construction contractors building buildings on time. Honestly, the sustainability of that whole enterprise, right? Are we going to keep the commitment in this country to, not only scientific computing, but to the science that needs the scientific computing? Honestly, that's my number one concern, because that's a political and a social problem, and those are always harder than the technical problems. The technical problems, if we beat on them enough, I think we can make them work. And we have a lot of people, really smart people, who really want to do that. So, but yeah, I mean, funding and follow through, like I said, at the drop of a hat, this project can move back a year. And I think very few people appreciate how complicated that is to do, right? I have a slot with a data center vendor to build stuff. We ordered transformers a while ago because it takes 2.5 years to get them. There's a lot of complicated moving parts. And so I think for me, that's it. I do worry, I think, on the technical side a little more. And again, even the technical problems are social problems, right? The sort of balkanization of the software ecosystem, where we have, because we went, roughly 25 years where there was sort of x86 and then x86 plus GPU and everything else was kind of noise, right? You know, there was some PowerPC, there was, you know, some ARM, there was a little Motorola, but really, you know, compilers and tools were locked in for that stuff. And, you know, we had a super reliable thing. Now we see sort of these very different paths for the sort of NVIDIA ecosystem, the AMD ecosystem, the Intel ecosystem, and then again, there's a lot of noise of people trying other things at the moment, but even those three big ecosystems, right? It's different compilers now, different tool chains, different programming models. That's really not good for the community, right? And to their credit, you know, the exascale guys are trying to bring it back, you know, to one tool chain that builds for all of them, but well, we still haven't seen if it builds for all three equally well. And Kokos and Raja are not the easiest entry points, right? For starters, they're not Python, which means they're never going to be the entry points for AI. So, yeah, so that, and again, it sounds like a technical problem that you have three different programming models, but really it's a social and a human problem. So, but that, the fracturing of those ecosystems, I think, could be a big problem for us moving forward. You're going to have three very different versions of Mbappage to build for those.
Thank you. And since you have already identified the names of your system until 2036.
Yes.
So 13 more years. So we look forward to working with you 13 more years. It'll be 30 years total, and then I.
Younger and better looking successor.
No, then I'll retire. Okay, then I'll retire. Okay.
You'll never retire.
Thank you. Let's give a big hand.